Hello, good morning. So today we're going to be looking at the average rate of change and looking at rates of change. This is a huge idea. This is at the foundation of calculus, which again is considered to be the greatest achievement of the human mind. So we're at the core of something really important. So I'm going to do my best to break this down into high-level ideas as well as fundamental principles, and then let the mechanics of computing these things come from the reading and the practice problems, because they're not less interesting, but they are it's what computers can do for us. What I really want you guys to do is to understand what a rate of change is, and be able to explain it to someone else, right? That's always the goal. We call it the Feynman technique, or the Feynman principle. We should be able to explain these ideas to a sixth grader if we really understand it. So I'm going to start with a basic question of how we measure change. I want to make the point that the main characteristic, what we care about most about a function, is how it changes. So then measuring that should be an important thing that we do. And then the average rate of change as a concept and as a formula for you to use on different types of functions. And we'll look at the different types of change that we can classify, something that changes at a constant rate or something that changes at a non-constant rate. We'll work with both in this course, and basically that will take you through pre-calculus and calculus, looking at functions with non-constant change, things that change differently per the input or over time. So first off, let's look at how do we measure change. So how do we measure change? Well, what do we mean by change? We mean how a value went from one to another. So if we think about a runner, and we're thinking about his change in position, that's a great drawing of a runner, by the way. We're thinking his change of position from where he started running to where he ended. So if he started at the 2-mile mark and he ran to the 5-mile mark on the track, how far did he run, or how much change was there in position? Right, he ran 3 miles is what your brain might be telling you. But how do we get there? Well, we took the 5 miles from the ending position, minus the 2 miles from the starting position. That got us a total distance of 3 miles. So this concept is how we measure change in general, which is the end value minus the start value equals the change. And how we use this idea in mathematical notation, for change we use the symbol delta. Okay, so we might say the delta in position P is equal to P2 minus P1. Right? If this is position 2 and this is position 1, then this is the change in P. So that's what we mean by this delta. This is equal to the change. Okay? So it's a big symbol. You see it in all different fields. You see it in psychology, sociology, chemistry, physics, biology. Every single science uses delta, and almost universally, I've yet to see a counterexample for this, it means change. And again, we're interested in change. The world is constantly changing. It's the one thing that we want to measure. If something's not changing, why would we measure it? So we care about change. And this is how we measure it. It's a difference, right? A difference of the end minus start. It uses subtraction. So let's jot that down just to kind of drive it home. We use the difference, aka subtraction, to measure change. In a quantity. Right? And this can be done even if it's starting from 0. So, like if we talk about maybe a population, of a new town, at time 1, let's say there was nobody here. As time went on, we see that now there's 1,000 people here. What's the change in the population? AKA change in P, we'll use the same variable here. Change in P, well, that's going to be the ending population minus the starting population, which we know is 1,000. Let's do that over here. 1,000 minus 0 equals 1,000 people. And again, it's going to carry the units of these quantities here. So that's the change in P. And again, it's P2 minus P1. Why is it backwards? Because we're going with the result minus the initial condition. Right? So this is how we measure change. We measure it with subtraction. So this is somewhat of an intuitive example, and maybe you could pause the video and come up with yourself and jot it down in your notes an example of something changing, some quantity in your life that's changing, whether it be money, time, growth, something that you are interested in. And think about how you'd classify its change. Would you do it differently than n minus start value? Probably not. There might be a few exceptions here or semantic differences, but in general, this is how we measure change. All right, so I don't mean to beat a dead horse here. It's a terrible metaphor. But I say this and make this point very clear because when we talk about a rate of change or comparison, it kind of ups the ante on this idea. So the first point I wanted to make was that we measure change by using subtraction. Second idea is that the main characteristic of a function is how it changes. So we haven't looked at too many classes of functions, or what we call parent functions, things that model phenomena in the real world. But for those that do, let me sketch a few out. For those that do, and you might have seen some of these things before, like the parabola here, and maybe another graph might be the periodic function, right, which measures things that oscillate. So you don't need to know what these are, but the idea of these functions changing over time or per unit of the input is what makes them interesting and is what makes them align to things that we want to model. Right? So the fact that this oscillates means it's not going to model something that's steadily increasing. Right? And the fact that this is steadily increasing in a certain way means that it's not going to be a good fit for something that's fluctuating back and forth, like the tides, right? Or the amount of hours that we're spending at a shop seasonally. This wouldn't be a good fit. So how a function changes is what makes it interesting. And if it doesn't change, then it's not a very interesting function, right? Like a constant function. Like y equals 7. Doesn't matter what x is, y equals 7. This has 0 change, right? Because the y value here and the y value here, the change in y, if this is y2 and y1, these are both equal to 7. This is 7 minus 7, which is 0. There's been no change in y because this is a constant function. No change. But how a function changes is what makes it interesting. But then there's this extra kind of degree of analysis when we want to talk about how fast something's changing. Not just how it changes, but how fast it's changing. So that's where the idea of average rate of change comes in. So the average rate of change, or what we call the Aroc, average rate of change, it comes in two flavors, constant and non-constant. Our next unit's going to focus on functions with constant rates of change, and then again we'll dip into things that look a little bit more like the functions we saw down here that have different types of change. This does have a constant rate of change, but this is not exactly what I mean. Functions can have a constant rate of change that's not 0. And here we were talking about just change, not a rate. So what is this rate word that we just brought up? Right? So if we want to become good mathematicians, things are not named creatively. They are named very precisely. Every word in math counts. We put a high premium on using words. It's not the way we talk, especially not me, but the way that we name things and write things down, we want them to be simple as possible, as abstract as possible, and that makes it elegant, and it also makes it the most applicable. So, what I'm trying to say is, we know what change means. What about these two words? Average rate of change. Well, let's start with rate. What do we mean by a rate? So some rates that we can think about are what? A rate of speed, velocity, a rate of payment, a rate of growth for an organism. And what does that mean, a rate? How does that differ from just the flat change of a quantity? Well, this is actually emanating from the word of ratio, which means fraction, which is everybody's favorite, right? So ratio is really what? It's a comparison, right, of one quantity to a next. So A to B, or Y to X. It's comparing one quantity to the next. So dollars per hour for wages, right? Miles per second for a bullet flying out of a gun. Or what did we say? Inches per year if we're talking about an organism growing. This is a comparison of two quantities changing. Inches per year, dollars per hour, etc. This is how we think about rates or ratios. So it's a comparison of two quantities of change. That's what rate of change means. And so lastly, why the word average? To say it simply, is that we're not doing it within an instant. We're taking an average rate of change because we usually do it between two discrete points, and we can't exactly know what happens just between those 2 points. Okay, so it's an average in that it's between 2 points, not at a single point. So the genius of calculus is what helps us get past the average and get a little bit more precise, but that's way, way beyond the scope of this course. Okay, so we are looking at the average rate of change, which says between 2 points, a comparison of their change. And how do we measure change? We do it by subtraction. So we have subtraction that measures change, and we're talking about a ratio, a comparison between two quantities of change between 2 points. So the average rate of change formula is equal to the change in the output over the change in the input. So we usually use delta y over delta x. And what does this mean? What does delta y and delta x mean? Delta means change, it means the difference. So y2 minus y1, your end minus start for your output over your end minus start for your input. So again, this might be, as an example, population change over time. End time minus start time. End population minus start population would get you the change in, let's just kind of cordon this up, change in the population over the change in time. And what would this tell us? This would tell us, on average, how fast the population is changing. So this is what I said before, a second order or another level of analysis. We could say before the population changed by 1,000 people, but we didn't know how fast that happened. Did that happen over 100 years, or did that happen over 3 months? Because that means more, right? That tells us more information about the phenomena of this town growing. And again, this abstracts to organisms growing, someone's symptoms diminishing over time. A lot of times we're interested in change per unit time, but not always, right? It can be whatever the input of the function is. So we've got a lot of big ideas here. Let's look to an example to kind of solidify this. So we'll look at my son Bowden. He weighed, let's say, 10.5 pounds when he was born. Actually, that's not accurate. He was 7 pounds when he was born. He was a little guy. He was 7 pounds when he was born, and he weighed 17 pounds at his 8-month appointment. So the question is, on average, how fast was he growing during this time? So a few things to note. This on average, why is this here? Well, maybe we'll unpack that in a little bit. But we're asking about how fast was he growing, which means we're talking about the change in weight over the change in time. Right? That means that dictates from here. Ooh. How fast was he growing during this time is the measurement or the comparison of the change in weight versus the change in time. That tells us how fast. So how do we measure this? Which we know this is the average rate of change. The change in weight over the change in time would be the difference in the weights over the differences in time. So we usually would say weight 2 minus weight 1 over time 2 minus time 1. Well, we need to come up with some values for these variables. So if we let W equal weight in pounds, and we let T equal, let's say, time in months, then let's pull some data from what we've been given. We have 7 pounds when he was born. This must be weight 1. He was 17 pounds at time 2, so that's weight 2. When he was born was given to us as like a verbal description, but what does this mean in terms of T? Well, we usually say, we'll say T1 equals 0 as a quantity, because this is when it began, right? So we usually start with 0 instead of starting with 1. So t equals 0 for when he was born, so 0 months. And time 2 was at his 8-month appointment, so that value is 8. So to compute the average rate of change, how fast did he grow? We take the change in the weights, so weight 2 minus weight 1, 17 minus 7 in the top, and again this is pounds, over 8 months, 8 months minus 0 months. And then we just evaluate and solve. So again, we have those implied brackets in the top and bottom, so we do these separately. So 17 minus 7 is 10 pounds over 8 minus 0 is 8 months. And sometimes you can leave it as a fraction that's appropriate. But here it would make more sense to get what we call a unit rate, which means we have the denominator as 1. So we just carry out this division, and 10 divided by 8 is 1.25. And the question is, what are the units here? Well, the units carry from the ratio of pounds per 1 month. Just like miles per 1 hour or dollars per 1 hour, 1.25 pounds per month. So to interpret this, again, this is the calculation piece. What does this mean? We can say on average, Bo was growing 1.25 pounds per month between birth and his 8-month appointment. So, a couple things to unpack here about this interpretation. This is really important. The first is the qualifier. This is on average, right? What I didn't tell you is that we had other appointments in between and that we also weighed him every day. He didn't grow 1.25 pounds per month, and we couldn't, distribute that evenly through each day. It wasn't a constant rate of change. It varied, right? Some days he was up, some days he was down. Some weeks he grew incredibly fast, and then other weeks he didn't grow at all. So the fact that this is an average tells us that we have imperfect information. Helpful still, yes, right? It tells us he's on a good path. He's still growing, but it is a limitation of this, and we might get more of a better picture of the growth and the speed of growth if we shortened the window. Right? I made that pretty big between birth and 8 months. Usually there's explosive growth for somebody in the beginning, and then they start to kind of taper off. So just kind of graphically to give you an idea of what I'm talking about, usually a baby will grow in a shape like this, right? So between 0 and 8 months, that's a pretty big gap, and we just measured this value here. So we missed how quick the growth was here, right? So anyway, the reason that we have to say on average is because we're between 2 points. So we're missing some data. And we also have in this description the quantity and then the units of the rate, right? And that English word per is really standing in for the division sign, right? So this is really the units of W over the units of time. And then the last part here, between birth and his 8-month appointment, this tells you the interval of values, right? Super important for the same reason I said before, that this is only really accurate during these 2 times, and it's still a limited interpretation, but we want to say that this doesn't apply outside of the 0 and 8-month appointments, because something might happen that's different from month 8 to 10 or something like that. So the kind of 3 parts that are here: the fact that we're talking about an average, the units along with the quantity of the rate, right, the value of the rate, and then the interval of values is specifically stated. So again, if we're talking about how fast a car was going, how much money you were making, how many dollars are being earned in a business per unit sold, we want to talk about the interval between 2 points, the interval of values, and what that rate was with units. Okay. So this is how we measure the change in a quantity compared to another, the average rate of change. In essence, it's the speed at which something's changing. But again, speed kind of breaks down when our input is no longer time. Change in output over change in input. So last idea I wanted to bring up here, and then you'll be kind of set loose on some practice problems to, again, be computing average rate of change and then interpreting what it is, noting the units, is the idea of a constant rate of change for a function versus a non-constant rate of change. So let's say for functions. And again, for functions, we only really care about how they change. So we can put them into kind of 2 categories: things that change at a constant rate versus things that don't change at a constant rate. Or we could say, to be a little bit silly, that their rate of change is changing, or how they change is changing. And that really mimics more what happens in the real world, right? Things that have a constant rate of change are pretty rare. Rare, but possible. So what do we mean by something with a constant rate of change? So an example might be you make $20 an hour, and that rate is non-negotiable. So no matter what you do at this company, there's no room for growth. It's always $20 an hour. So no matter how many hours you work, it's going to be that many hours times 20 is how you get it, or is how much you get. So that is a flat rate or a constant rate of change. Okay, it's different from 0. You can still have a 0 rate of change, but that's really not too interesting, right? But we might say that, let's see, size of my monitor, right, is always going to be 20 inches. It's never going to change no matter how much time we move forward. The change is not happening. So, 0 inches per day. That is a constant rate of change. It's not very interesting though, right? Why would I measure my monitor size over time? Maybe I'd be going crazy. But more constant rates of change that we'd be interested in. We have a wage. We might have something like a constant speed of, let's say, 25 miles per hour in cruise control, right? So if you're in a car and you set the speed to 25 miles per hour and you stay in the right lane, over a period of time, you might have a constant rate of change of just 25 miles per hour. You travel 3 hours rather, and you've gone 75 miles. You travel for 4 hours, you've gone 100. It's a constant rate of change. How these things look for the $20 an hour rate, it might look something like this. Y equals 20h. For 0 inches a day, what would this function look like? Well, it'd look like it's sitting right on the x-axis. Y equals 0x, which is just y equals 0. And then for 25 miles per hour, for graphing distance over time, this function might look like this, very similar to above. D equals 25t. Now you don't need to know how I came up with these. We will do that later. But this is how these look. And what do you see as their characteristic? They are straight lines. All right, their graphs are straight lines. And the same can be said for something that might be decreasing. Right here, all of these were increasing or staying flat. But if we had something else that's changing, like we're losing $100 a day on our app. On our app in the App Store. Let's say it costs a certain amount to host an app in the App Store. So what would the graph of this look like if we have our profits versus time? Might look something like this. P equals negative 100t plus 1,000. Again, don't worry about where I came up with that, but you see that this is a decreasing graph, and the way that it changes, the change in P over the change in T, is the same wherever I go. It's always going to be negative $100 per day. And this here, the change in distance or the change in time, the average rate of change will always be 25 miles per hour. Same here and same here. So these are what we call constant rate of change, and it's the key characteristic of a function that we call linear functions, because it's a straight line. And this is where we focus in on chapter 3, so I'm not going to go too far into that right now. Linear functions are super important. They're the most important function. I said that they're simple and rare. I'm talking about in terms of physical phenomena, but what we use linear functions for is to approximate things, and if we zoom in far enough, things start to look linear a lot, so it actually becomes a super important tool that we can use as long as we're careful. We use it a lot. But functions with non-constant rates of change. Some examples of that. Population of deer fluctuates between 1,200 and 800 each year in an area. How would this look as a graph? Might look something like this. And so, how does this differ from the other graphs we saw? Well, based on the difference between 2 points, if this is population, this is time, my delta P over delta T here versus my delta P over my delta T here, let me do it in a different color. We see that this rate of change, let's say it was approximately 5, and then this rate of change over here, and the second one, was like -10. And what are the units here? Maybe deer per month. So the average rate of change during this interval is different than the average rate of change during this interval, or the way that the population's changing. It's changing at a different speed and in a different direction, right? Up versus down, based on where we're at. So this is a non-constant rate of change because it's not always the same like it is over here. So what I was saying before, and this is a big math concept, so it doesn't need to make total sense right now, but most things in the world act like functions like this that have non-constant rates of change. Not that everything fluctuates, but that things might be shaped like a parabola, or might do something like this, which looks like exponential growth, if you've heard of that before. Especially, in the shadow of the pandemic, we definitely have heard about exponential growth and spread. And so we can look at the average rate of change over time and see that it's changing. And how that change is being affected or is increasing or decreasing, that tells us something about the relationship. That's super, super important. All right, it is the most important and interesting thing about functions. So if something has a non-constant rate of change, that means that it's not linear and that how it's changing depends on where you are and the interval, whether that be time or values for the input. So I want to stop it there. I want to give you a chance to go in and compute some average rates of change, to remember to bring the units along like I've been doing here, and then to try to, again, make sense of what this really means it's a ratio of differences. We measure change with subtraction, and we measure this rate of change, how fast it's changing, or how it's changing in relation to the input, by comparing them as a rate. Okay, so I hope you enjoyed that, and we'll see you in the class discussion with all and any questions.